So I'm going to talk about an implementation of streams in DisCoPy. And the previous talk was about streams, so it's perfect. And so DisCoPy is a library for monoidal categories. And I'm going to start by introducing monoidal categories and how you implement them in Python. And I'm going to give a couple of examples, like how you implement the category of functions, of matrices, of tensors, and how you implement the free monoidal categories. So these are categories of string diagrams. And also from string diagrams, how you can define a functor that interprets the string diagram in a semantic category, like the category of functions or matrices. Then I'm going to talk about how you can extend this to implement feedback monoidal categories, and how you can build monoidal streams over any of these monoidal categories. So this is an implementation in Python, and we're not so concerned about like correctness or like formal representability. One of the advantages of using Python is that you have a whole series of libraries, of well-established libraries for machine learning, tensor computation, tensor computation, tensor computation. Tensor computation, or probabilistic programming, quantum computing, quantum computing. One of those categories. Sorry, it's okay, it's okay, it's okay. At some point, I'm gonna, yeah, that's good. So let's start after this person sits down. All right. So how do you implement a monoidal category in Python? It's very simple. You just need two classes, one for the objects and one for the morphisms, and a few methods. So for the objects, if you want just a category, you don't need any methods. It's just some class that stores the object. If you want a monoidal category, then you need to define a tensor product. That's a method that takes the self, so the object with some other of type object, and gives you an object, and then a unit that just returns a particular object. In order to implement morphisms, so a morphism is defined by a domain, which gives you an object, a codomain, an object, and then you will have like two methods for composition. So we call them then and tensor. Then is the sequential composition morphisms, and the tensor is just putting the two morphisms in parallel. And then you need a static method. A static method is just a method that doesn't take self, and you need a static method that, given an object, returns a morphism, gives you the identity on that object. So this is kind of the interface that you need to define a category. This is an abstract class, so it doesn't have, I mean, I can't even initialize an instance of this class. So let's look at a simple example. The class of functions. Python functions. Just a microphone.
Yeah, it might be.
Hello, hello. I mean, I'm also listening to my talk, so it's fine. Like mute. Hello? No. No, it's okay. It's okay. It's okay. It's okay. All right. Sorry about this. Still here. So, how do you? Okay, we've seen how you implement just a monoidal category. You need a pair of classes and this interface that allows you to get domains and codomains for each morphism and compose them in sequence and in parallel. So, for example, we can build the class function. A function is initialized by just a Python callable, so just something you can call. And it has a domain, which will have type tuple of Python types. So type is the label for Python types. And you can take, so the domains are going to be tuples of types. The codomains are going to be tuples of types. And then you need to define the composition, the tensor product. This is all done already in DisCoPy, for example, but it's very simple to do. And you can just define, so the objects, for instance, X, Y, Z, could be int, complex, and bool, 3 types in Python. And you can define some functions. So really, this function class is a wrapper around the callable class of Python. You will initialize it by giving it a function and some domain type and a codomain type. And then when you compose them, and you can compose them with this syntax here, with the syntax at the bottom, the composition is given by this thing. And yeah, when you compose them, it's gonna check that the types match. That's basically all it's doing. And also, when you put them in parallel, it's gonna apply the function on one part of the, like, it's just gonna do the right thing. So you have like a tuple of types, a couple of functions, and it's gonna apply the functions on the right part of the tuple. And now we cannot check equality of functions in Python. We can only check for certain input values. So here, for instance, we're checking that they're equal on 54. And we're checking that associativity holds on the input 54. That's kind of the best you can do for the category of functions in Python. Obviously, functions or in Python are not really a category because they could have side effects, they could have other, I mean, you can't check equality, right? So in general, if you restrict yourself to pure functions, then you can get just this observational equivalence on some contexts. And so the category, let's look at another example. The category of matrices could be implemented simply by having the initialization given by a NumPy array, and the domains and codomains will be of type int. So in this case, if you take 3 matrices, you just define them by giving the list. The matrix class in DisCoPy automatically converts them to NumPy arrays, and you just have to give the types. So in this case, it's a vector, so it's a matrix from 1 to 2 for F, and then you have G, a matrix from 2 to 2, and H, a matrix from 2 to 1. You can compose these 3, and you can check associativity. In this case, it's going to check the quality of the matrices you've constructed, and you can check it exactly. So here, this is the category of matrices, and you can, the tensor product is going to be given by direct sum, so just by summing the integers. gonna call the add method of int. But you could define a category of tensors, which is a subclass of matrix, but now the domains and codomains are not given by just an int, but by a tuple of ints, which are all the dimensions of the tensor. So some are going to be inputs, some are going to be outputs. And for example, you could implement a subcategory of tensors to be such that they are stochastic matrices, so that you can sum the rows and columns and get always one. And this would be just, I mean, implementing a subcategory is just giving a method that checks whether the morphism is in that subcategory. Yeah, so there's this important concept in Python. You know, if something it works like a duck and like quack, 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 quack. If it quacks like a duck, sorry for this. This is worth 50 pounds, so it must be a duck, right? If something works like a duck, and it must be a duck. The same concept, right, holds for functions, and I mean, if something adds like a rig and it multiplies like a rig, then it must be a rig. So what it means is that we can define the class matrix over any D type as long as the D type has some method add and some method multiply, matmul. So there's this is implemented in DisCoPy. I mean, in Python, there is a concept of a class generic, and in DisCoPy, we had to implement name generic, which basically just, instead of being just a type annotation, it also stores the D type or the thing you give it as name generic in the object, so that you can, if you initialize a matrix of int, you can check the D type, and that's very useful in a lot of applications. So if you define a matrix of int with like 0, 1, so a vector 0, 1 in int, it's going to be different from the matrix of bool with 0, 1 of the same type with the same matrix. Whereas if you did this in Python, you would get that the two are equal. Okay. And what's nice is that, okay, now you can define, well, you just have to give morphism an addition and a multiplication. If you define the multiplication to be the composition, and you have a way of summing morphisms, then you get the free byproduct completion on the category. So if you have a category enriched in sums, then you can do matrix of that, and you get the free byproduct completion. You're doing matrices of function of morphism compositions. So how do you implement free monoidal categories or string diagrams? First, you need a class for the objects. In this case, they're types. They're going to be a tuple of labels for each type. So strings. You can define the tensor to just concatenate the tuples. And you then define morphisms. The way we define them is as lists of layers. So a layer is just a box, is just something that looks like this. It's a box with some types, some identities on the right, identities on the left, with some types. So it's just a pair of types, Y and Z, let's say. That's a layer. And you can define whiskering. So every time you have an object, you can put it on the left or put it on the right. That's just answering by identities. Okay. Then you define a diagram. A diagram is going to be initialized by a list of layers. So and it has a domain type, tuple of str, and a codomain type. It has a static method, the identity method, which is just the empty list on the type. So there's no layers. And then you define composition of diagrams to take, just the diagram itself and the other thing you're composing it with. It checks that the types match, and it constructs the diagram, which has the domain of the first, the codomain of the other, and it concatenates the layers, right? So this is an implementation really of pre-monoidal diagrams, not, or pre-monoidal categories. And we'll see, but before I tell you about like how you can get equality of diagrams also in as monoidal diagrams, there's kind of a trick that I've skipped over. So here, we've defined a layer has box of type morphism, and inside the layer, like this box, we kind of want to treat it as a diagram. So we need to basically define it after we've defined that diagram. So we define the generators of the free monoidal categories after we've defined the classes for the morphisms. So a box is a diagram. It has a name, and it initializes the diagram with just itself in a layer without anything on the left or on the right, with its domain, with its codomain. So it's just a very simple thing, but it allows you to have on the nose equality of like the box is the same as the box composed with an identity, or yeah. So this is kind of important, that you don't want to have that this equation doesn't hold. So you can draw diagrams, of course, and you can, there's been actually a lot of work in DisCoPy for the drawing to be beautiful, like Alexis has done some crazy, he's the master of drawing diagrams, for sure. And yeah, so here there's two ways, for instance, of defining a diagram. You could define it with the syntax here, like this is the syntax that we've seen also before. The composition is just this, how do you call it? I don't know. Chevron. And the tensor product, we're using the at symbol. But you can also define diagrams with function syntax. So in this case, right, it's pretty simple. B and C, you define the output of F, and then you return G of B and H of C. So this is just a syntactic thing that you can do with this from callable method. So you just define your function at this decorator, and you will get the diagram directly. The diagram stored as a pre-monoidal diagram that then you can draw and use in DisCoPy. So I mentioned this before. We have pre-monoidal diagrams, and if we want to check equality up to interchanger, we've defined a normal form method, which basically interchanges everything to the right, or it could be to the left. But this is was proved in a very nice paper by Vicari and Antonin Delperch about normalization of planar string diagrams. When the diagram is connected, so it has just one connected component, then you can just interchange to the right, And that will give you a normal form, so you can check equality by just taking the two diagrams, interchanging them to the right. And so this diagram that you see on the board, like this, is the worst case of the interchange normal form. Is like all these diagrams are equal as monoidal diagrams, and yeah, to check equality of the two ones where the state and the effect are either outside or inside, it takes cubic time. So that's the worst case. It takes cubic time at the worst time, and more in general, usually it's very fast, you know, obviously. So we've seen how to define some concrete categories like functions, matrices, tensors. We've seen how to define free monoidal categories, string diagrams. Now we want to interpret the string diagrams as concrete computation. And in order to do this, we need functors. So here in DisCoPy, we define functors only from free categories, or I mean, you could define them on any category, but then you need a way of looking at the function and deciding what to do. But when you define them from the free monoidal category, you can define them simply by a for loop. You go through the list of layers and you apply the function to each layer. So a functor is going to be first initialized by a codomain. So here, the codomain could be just, again, the free monoidal category. Here, putting equals category tie-dye just means by default, that will be the type of the codomain of the functor. But if you could give it category, type, Python type, function, as we've defined before, and you get a functor into functions. So then you need two mappings, ob and r, one that goes from the objects of the free monoidal category, so just actually of the free monoidal category, the basic objects, not the tuples of strings, but just a single string. You have to return for each object an object in the codomain category. And you also need a mapping on arrows. That's enough to define a mapping for the instances of box, and you will get the mapping on the full diagram. So that's going to be implemented by the call method that you can apply to both types and diagrams. And that's an example. So the diagram that we've seen before, we could interpret first on objects, we interpret X as int, Y as complex, Z as bool. And then on arrows, we can interpret F as three maps, and then we can apply F to it, and we can check here functoriality. This holds on the nose. Yeah, so then you can check that functoriality is true on some particular input because you're giving a function. So I think this was an overview of like the main concepts of DisCoPy. We have syntax, we have semantics, and functors between them. And so there's this beautiful paper by Peter Salinger with this hierarchy of all the graphical languages. And this was a big inspiration for us, and we implemented a subset of this big hierarchy. So you see here, these are all the modules in DisCoPy that implement some of the hierarchy. So I guess at the top you have just categories and monoidal categories and then you can have, so all the syntax part ends at like, is inside the box. So these are all different. Well, in order to just, you have the monoidal diagrams, and then you can add structure by adding static methods that generate, that give you the structural morphisms of your category. And then if you want to have check equality, then you need to implement a normal form method for that class, or some way of checking equality. So in particular, we implemented it for monoidal, closed, rigid, pivotal, ribbon, no. No, because it's gonna be, well, ribbon is fine. Well, I mean, braided, for instance, is like you get knots. So it's balanced, you get knots. So there it becomes already really hard to check equality. But so we have these kind of syntactic categories, and then some basic semantic categories that you can interpret them in. And obviously, not all syntactic categories can be implemented in any concrete category. So like, you know, when you get to, if you have caps and caps that get from rigid, and rigid is where you get the caps and caps. And then all the things that are in the future in this DAG cannot be interpreted in functions, but they can be interpreted in tensor, for instance. And it's gonna raise an axiom error, say, no, you're trying to implement a cap as a function, and that's not possible. And then we've developed some application, but a lot of the work was in the development of the hierarchy and semantic categories. And it has a lot of interfaces with like well-established libraries. Like for quantum, we have Ticket, ZX, we have interfaces with Penny Lane, with tensor contraction. Yeah. So there's a lot of stuff in there. So now we get to the point of the talk. So we want to implement, well, up to now we have a picture of computation as a one-shot computation. Like in a plain monoidal category, you just have a morphism that defines a computation that does one shot, you get the output, you're done. But we want iterated processes, and we want to look at families of diagrams and families of processes. And to do that, we implemented monoidal streams. And in particular, yeah, what was presented in the last talk by Elena. And so here, this is the syntax for streams, where you have, yeah, just a feedback monoidal category. How do you implement this syntax? You can just, basically, this feedback is a subclass of box. It's gonna wrap around, so you just give it as argument a diagram. It's gonna check that that you can take the feedback, and then it's gonna change the domain and the codomain because it's taken the feedback, and it's gonna return a box now in the diagram. And you can draw it, and you get this diagram on top. Then, in order to implement monoidal streams, we get back. You remember the DAC? Well, streams can be implemented over any base monoidal category. So you take a class of objects and you apply tie of it. Tie will do, well, is defined by a base. So it has a base object, and then it's just a stream of these objects. So it has a noun method that gives you some object, and it then has a later method that gives you a so-called thunk. So just a callable from the empty tuple. So that just waits before, or you need to call it before it starts going to the next element of the stream. So that's a way of not like unfolding the whole thing as soon as you initialize. And so this way you get streams of objects, and that's simple. And then if you want to define streams of morphisms, the way, well, we've implemented intentional streams. So you need to give, in order to initialize one, you need to give a morphism for now, a domain, which is a stream of types, or a stream of objects, codomain, which is another stream of objects, a memory, which here is another stream of objects. And so we kind of have it explicit what the memory at each time step is. We haven't quotient by dinaturality, for instance, or observational or co-induction. This is hard, like this is, yeah, same reason that we don't quotient by equality for functions. Here we cannot. And then we define the later is just, again, a stream. Yeah. So what you can do, if you take stream of diagram, then you can get an unrolling. So this class stream comes with a method unrolling that you give it an integer time step, and it gives you the unrolling up to that time steps. So if you define the diagram like this, then you can unroll it for 3 time steps, and you get this diagram. That's for the syntax side. And then we can interpret this in some semantics. So here's an example of a feedback diagram you can draw. It's a diagram for the Fibonacci sequence. When you take the the feedback of the swap is basically waiting 1 time step. This actually, yeah, so you can interpret each of the boxes in this diagram as functions, like the 1 as the element 1, the plus as the addition, and then you know, this is done by this functor syntax, where like you map each box to some function, and then you can unroll 10 time step, and you get this Fibonacci sequence for 10 time step. And then, well, you could put any functions in there, right? So again, using the category function, you can define a random walk by first building this diagram that represents, right, so it's 0. So the first output will be 0, and then it's followed by some random generator of either +1 or -1 added to the last element in the stream. And this way, if you unroll it, then for 8 time step, it's going to generate 8 random numbers and make a random walk of 8 time steps. So yeah, I think maybe I'm in time. I don't know.
Yeah, that's maybe.
Yeah, I'm finished.
Quick question. So in computer science, you talk about streams. Is the stream that you later talk about sort of I want to say it gives you the other type of stream is like signals in reactive programming where you subscribe to like what you do something next, like tell me, and then it's like, you know, they're coming from some maybe the user moving their mouse and you're subscribing to mouse. And then, you know, the way people do this, I don't know, sub development is you have a bunch of like input streams, and then you process them, and it has a very similar vibe to streams, but it's both upstream rather than downstream. Have you thought about this stream at all? Or,
Yes.
Yeah, it also falls under like incremental programming.
Yeah, it feels a bit like asynchronous streams, because
Yeah.
you would have to wait for someone to click before you actually do something. Yes, so that's definitely something I've thought about, but I mean, in the applications that we have in mind, in particular, like for categorical quantum mechanics, we really kind of want this, discrete time steps, synchronous thing, and also for the moment, I don't know of a categorical method for doing asynchronous stream. So really, DisCoPy is like taking things that are done with good theory and implementing it, because once you have the good theory, you can implement it in DisCoPy. So it's kind of the point. When you write a paper about the asynchronous streams, we will implement it.
Okay, that's thank you.